Hello, I'm Sumukh from the AMD compilers team. The topic of my presentation is vector data dependence graph for better visualization and verification of LLVM-IR. My team members include Raghesh, Ruman, Karthik, Aishman, and Meena, who have also greatly contributed to this project. So the presentation is structured in the following manner. We'll be going through each of these topics one by one. Let me start with the introduction. As we all know, vectorization is an efficient technique which brings great performance improvement and takes advantage of performing the same operation on multiple data elements simultaneously, thereby creating great performance improvements. However, visualizing the same vectorization in the form of a data dependence graph could be a difficult process due to the modification of the data flow as well as presence of vector lanes due to the parallelization that is being performed here. Thus, our project aims to tackle this challenge by providing an extension of the existing data dependence graph by providing a visualization for the same, as well as utilize the constructed graphs to verify the vectorization that has been performed. So let us consider the following example. Here we have a combination of instructions that greatly modify the data flow. Now, if you look at the original data dependence graph, we acquire no information about the shuffle instruction which performs modification in the data lanes. Neither do we get information about the lanes from which the extract elements derives its values. However, now consider the graph that our pass produces. We can clearly see a lane-by-lane dependence between the instructions as well as the data flow which is clearly represented, making it easier for us to understand the vectorization that is happening here. In addition to this, we also plan to remove the glue instructions such as the shuffle instruction, which add no logical dependence to the program logic and make the graph even simpler and further reduce the complexity of the graph. Now, that was the visualizer part. With the verifier part, let me start with the following example. Let us consider two incoming values, P0 and P2. What we try to do here is compare the existing scalar DDG graph and the vectorized DDG graph. This process is not that straightforward. So in order to make it simpler, we are actually going to scalarize the vector DDG that we have created. So by scalarizing, what I mean is a single vector instruction is going to be split depending upon the number of lanes it has into nodes of its own. So for example, consider the first vector load where it has two lanes, VL0 and VL1. This is going to be split as individual nodes of their own, which can be seen in the second image, and so on. So the same procedure is followed for all the vector instructions that are present in our graph, and we result in a scalarized DDG, which can be used for a one-to-one comparison with the original scalar DDG. So in addition to the data dependence that we are representing, we are also going to ensure that the memory dependence edges are depicted accordingly. If we see that in the original graph, we understand no information about how the memory dependence exists between the two nodes, whereas in the second graph where we are going to scalarize the DDG, we observe a clear memory dependence between the first lane of the vector load and the 0th lane of the vector store. So we ensure that we retain both the data and the memory flow dependence when we scalarize the vector DDG. Now, we arrive at the main definition of our algorithm for verification, which is nothing but, given the assumptions, a vector DDG is equivalent to the scalar DDG if and only if there exists a path in the scalar DDG for every path in the scalarized vector DDG. So this algorithm aims to derive a one-to-one mapping between the two graphs that we are trying to verify. The elements that constitute our graph are as follows. We have the nodes, which can either be the scalar instructions or the vector lanes. And then we have the edges that are either the data or the memory dependence. The assumptions that are needed in order to ensure that this verifier produces a right result is that there are the same instruction sets on both the scalar DDG side as well as the vector DDG side. And we should also ensure that there are no non-trivial transformations that are being performed on the vector DDG, because that would result in elimination of some of the nodes that we would have otherwise compared the graphs with and would lead to a wrong result. So this is a brief description of the algorithm that we follow, where we take the two graphs and traverse them in the topological order, and we perform a level-by-level comparison. The incoming values are first compared, which form the roots of our DDG. Once these values are compared by the method of induction, we can just ensure that the two nodes of the corresponding graphs are equivalent by ensuring that the parents are identical as well. Once this comparison is successfully done and the instruction sets on both the sides are exhausted, we can conclude that the graphs are equivalent. However, if the match fails at any point, we can say that the graphs are not equivalent. So here is an example that shows us the differences between the two graphs. So here in the scalar graph, which is on the top right, we have incoming values from P0 to P3, followed by 4 scalar loads, and then 2 scalar additions at the end. We can see that there is the scalarized vector DDG also looks quite similar to how the original scalar DDG looks like. And it also has the lanes depicted as nodes of their own in the form of VL0 and VL1 for the first vector load and VL2 and VL3 for the second vector load. The comparison is pretty simple, where we first start with the roots of both the graphs. So we compare P0 to P3 on both the sides. And once that comparison is done, we move to the corresponding level where VL0 is compared with L0 by checking for the parents of the node, and then so on until we arrive at the end of the leaf nodes, following which we can conclude that the verification process is completed and the vectorization holds true. So I would like to talk about the soundness of our algorithm here. In our case, if the verifier actually concludes that the result is equivalent, then we can actually say that it is equivalent. But however, if it decides that it is not equivalent, it could go either ways. So the verification procedure is sound in nature. However, the non-equivalent part is due to the fact that there are certain special instructions in the vector DDG part, such as the shuffle instruction, the extract element, insert element, for which there is no correspondence in the scalar DDG. Even though we handle these special instructions, there could be other anomalies or other combination of instructions that could be difficult to judge, and it would require further reasoning from our side to ensure that the two graphs are actually equivalent. Hence, in those cases, we actually return the result as non-equivalent, thereby making our verification a sound procedure. In the future work, we plan to propose this as an RFC to the LLVM community as well as to the Google Summer of Code project for further development. We also need to ensure that the visualizer that we have needs to be concise in nature, and the view could be very cluttered for very dense graphs. Thus, we need to also represent subgraphs in a form where we could understand the graphs in a simpler manner. And this verifier is currently only for the SLP vectorizer, and we need to extend the support for the loop vectorizer as well. Thank you.